Hey, I'm super excited to talk to you about RLHF, DPO, and KTO today. These are all ways to optimize AI models, and we're going to approach them from a pretty high level, explaining the use cases and the benefits of each one, and why the researchers were even motivated to come up with them. So hopefully by the end, you'll have an idea of which ones might be useful to you with your AI engineering projects. I'm going to start with this little graphic just that shows you how a model starts with pre-training, and then we do supervised fine-tuning on top of that to turn it into a chat model. At the very top, these are the final steps. And as we move up this pyramid, we're using fewer tokens and more refined data. So that's really what you need to have, is a strong foundation of a model to start with. And then you can apply these techniques to really optimize them and just make them that much better. Now let's get into reinforcement learning from human feedback. Let's start with this term reinforcement learning. You can think of that as training a model through trial and error in a dynamic environment. And I think back to my Psychology 101 class in college. We actually learned about this with mice and experiments. So researchers might train a mouse to go through a maze, and they put little pieces of cheese throughout the maze, right? And as the mouse follows the cheese and smells the cheese and feels happy eating the cheese, it's also learning how to do the maze. And that's a good way to think of reinforcement learning. In this case, the cheese is the reward. B.F. Skinner actually coined the term reinforcement in 1937. And in machine learning, reinforcement learning, of course, isn't done with cheese. It's actually done with math equations. And the rewards are calculated with an equation. So that's how reinforcement learning can be applied to games and other, call them dynamic environments, where you essentially set it up so that an equation is giving the model feedback, but it's learning through trial and error. Now that brings us to RLHF, the HF being human feedback. And this is very specific. So it's a feedback loop in which a model generates outputs that are scored by another model and fed back in for fine-tuning. This was actually motivated because researchers wanted to be able to do more with less data. So they said, let's automate this reward calculation so that we don't need as much human feedback to train the model. So in this paper from 2017, Deep Reinforcement Learning from Human Preferences, they say in order to practically train deep RL systems with human feedback, we need to decrease the amount of feedback required by several orders of magnitude. What they do is they sample human feedback, train a model that can hopefully generalize that human feedback to be able to provide it in place of humans to a model that's learning in this dynamic environment. Now, there's a bunch of terminology around this that I'll explain here, and this will help you if you end up reading any of these papers in the future. So policy is the desired behavior for your model. It's like, I want my model to follow this policy. Well, they're kind of using that term policy in place of the model, typically. So in your head, just substitute policy with my final model or my model that does what I want. Now, the reward model, I explained rewards with the mouse and the maze, but the reward model is this separate model that scores or ranks outputs. And then you need the RL algorithm or optimizer. These are the math formulas that determine how to update your model based on those rewards. The most common one for RLHF is called PPO, Proximal Policy Optimization. And I also want to touch on this KL divergence penalty or clipping. Essentially, this is part of the optimizer or RL algorithm that prevents the model from gaming the system. It's like if the model figured out a cheat code it could use that just gets really high rewards. If you don't have this penalty or clipping in your formula, then the model can kind of go off the rails, maybe repeating a single word or saying gibberish that just kind of games that reward model. So this prevents that from happening. RLHF in a nutshell looks like this. You start with your preferences data. That preferences data is used to train this reward model. You have your instruct-tuned model, your supervised fine-tuned model that you make a copy of, which will become your policy model. You'll sample the outputs from the policy model, and then the reward model will tell you the scores. And the scores will be fed into the PPO algorithm along with those prompts and the outputs, and that's used to make updates to your policy model. And then there's that constraint between the original model, the instruct tune model, and your policy model to make sure that each update you're making is not taking it way too far. So you're making lots of small incremental updates. There's a lot of variations to this process. So there's online or offline. You can essentially do it all offline where you sample the outputs from that policy model, you score them and you make all the updates in one go, or you can do it iteratively where you're sampling the outputs, you're changing the weights, and then you're using the updated model for each subsequent sampling. There's different types of algorithms you can use. So PPO is the most common for RLHF, but there's P3O and others. You can choose which model you want to use for the reward model. For example, in some papers, they say, hey, we had good success using the same model that we are using for the policy model. It knows the same things as the policy model, so it's capable of scoring it. You can choose how to train that reward model, how to evaluate it, what hyperparameters to use both for the reward model and for the policy model. And of course, how long do you actually want to run it for? When do you stop? So lots of choices. RLHF is really more of a framework than it is a prescription for a particular way to train the model. Challenges with RLHF are many. So it has a reputation for being unstable, can be hard to tune. It has lots of moving parts. There's more potential there for problems to arise. It's time consuming to sample outputs from the model. And then it's still expensive to have humans label the original preference data for you. Sure, there's off-the-shelf data sets, but then why is your model going to be better than anybody else's model? And then human preferences vary. There tends to be internal inconsistencies within data sets that can make it harder for the model to learn. Imagine you have multiple data labelers using their preferences. They're not all going to have the same preferences. Even if you give them instructions or a rubric to use, there's going to be, this person liked that one better, but if you handed it to another person, they might have liked the other example better. Those types of variations make it tricky to mathematically teach a model what's important. Now let's talk about DPO, Direct Preference Optimization. It's an algorithm that trains a model on preferences data directly. So we're talking about the same data, and we're going to make it really direct. And here's the paper, Direct Preference Optimization. Your language model is secretly a reward model. So they say, in this paper, we show how to directly optimize a language model to adhere to human preferences without explicit reward modeling or reinforcement learning. So there's no trial and error, and we don't have a reward model. That's why it's called Direct Preference Optimization. It is mathematically equivalent to RLHF without having to train a reward model or sample outputs. Just to make this really concrete, let's take a look at what a preferences data set actually is. So in the left column, we have prompt, and then we have a chosen output in the second column, and then final column, a rejected output. So chosen and rejected represent my preferences. The prompt is the same for both. What is the capital of Colorado? Denver. I prefer that over, I can't answer that because I'm a useless language model. Just not very helpful. Now, write a funny joke. Why don't oysters donate to charity? Because they're shellfish. That made me smile. Knock knock jokes, I'm not a huge fan of, so I rejected that. Sorry, knock knock joke fans. So you take that data set in DPO, and then you have your instruct tuned model, just like we started with RLHF. And you're going to copy that instruct tuned model to start the starting point for your optimal policy model. And then you're going to run the DPO algorithm with your data set and make updates for that data. And then there's also going to be that KL divergence term that constrains it from diverging too far to prevent the model from gaming the preferences data. And that's really all there is to it. They figured this out mathematically to get really the same or better outputs as RLHF by using that preferences data, which was really the goal of RLHF in the first place, was to be able to use less data to train a model. And they figured it out, how to do it with math. It's awesome. It's way simpler. It's faster than RLHF. It's more reliable. It has better performance. And this, I think, is super interesting. DPO trained models respond more consistently to higher temperature. I have another video where I talk about temperature. It's essentially how random the outputs are from your model. And DPO trained models are more robust to changes in sampling temperature than RLHF trained models. This is what that looks like, a graph from the paper. The yellow line at the top is DPO. On the y-axis, we have win rate, so higher is better. And as that sampling temperature increases, it does not come down too much, relatively speaking. If you look at the pink line, the PPO trained model, which remembers the optimizer algorithm from RLHF, it just dives. So I think that's a really cool indicator that DPO somehow trains the parameters in a way that even when it's more random, it's making better choices with the next token prediction. There are still challenges with DPO, but they are essentially a smaller subset of the challenges with RLHF. So human labeled preferences data is still expensive, and preferences can still vary, and that internal inconsistency within datasets can make it harder for the model to learn. So now we are going to talk about Kahneman-Tversky Optimization, KTO. KTO is an optimization algorithm, like DPO, inspired by behavioral economics, which I think is really cool. And it's inspired by these guys, Kahneman and Tversky. They are legends. Kahneman won the Nobel Prize in economics. Tversky and Kahneman worked together for about over a decade, I believe. Together, they created prospect theory, which was cited when Kahneman won the Nobel Prize. Kahneman wrote this book called Thinking Fast and Slow. Maybe you've seen it. These two have done some amazing work. They are not the ones that created KTO, but it was named after them. And it was inspired specifically by this prospect theory that they worked on. So prospect theory is this idea that the perceived value of losing something you already have is greater than the perceived value of gaining the equivalent amount. In this chart, we show the perceived value on the y-axis. And on the x-axis, to the right, there's a gain, like if you're offered 5 cents. Or on the left, if you were going to lose 5 cents. And what Kahneman and Tversky figured out was that people place much more perceived value on losing 5 cents than gaining it. So that's why it's steeper on the bottom left quadrant going down and not as steep going up in the upper right quadrant. So people generally prefer smaller, more certain gains than small chances at big gains. This is crazy, right? Why are we talking about economics? But if you're training a model to adhere to human preferences, then you want it to kind of learn like a human, right? So they took this concept and they created KTO as this optimization algorithm. And it takes some of these things into account. So KTO seeks to maximize the utility of generations by considering the tendency of humans to be risk averse. Now, it is inspired by prospect theory, not derived from it. So KTO specifically borrows the concept of a value function with a reference point from prospect theory. And then there's this other part of prospect theory called the weighting function, which is specific to psychology, and so they didn't use that part. So they picked and chose what seemed applicable to the machine learning problem. And then in KTO, they use a sigmoid function instead of an exponent in its value function, which graphs similarly to the value function in prospect theory, but is easier to optimize. So I actually thought it would be interesting to look at these two side by side. So you have a sigmoid function on the left and you have the value function from prospect theory on the right. You can see they're both kind of the same shape. So it's the same idea, it's just not literally the same function. Now, a KTO dataset is a little bit different from the DPO dataset. What it requires is a dataset of desirable and undesirable outputs. So these are very common in the real world, which is great. Think of likes and dislikes. Like, I see something I like, I give it a thumbs up. I see something I don't like online, I give it a thumbs down, right? I could be feeding a data set for a KTO because I'm indicating if I like or dislike something. This type of data set can actually be inferred from our preferences data that I showed you earlier, effectively doubling the size of the data set. And I'll show you that here in a minute. What's cool is that this works well even if your data set is unbalanced, so you don't need to have the same number of liked examples as you do disliked. In the paper, they tested 9-to-1 and they still got really good results. Now, remember that DPO data set? We had one column with a prompt, we had the chosen and the rejected columns. So now we're talking about splitting that into likes and dislikes, or desirable and undesirable. And in the KTO data set, we have the prompt, and then we have the output of the ones we liked. And then on the right side, we have the undesirable, the prompt, along with the output that we didn't like. So that's one naive way to kind of split a preferences data set into likes and dislikes. There's, of course, a lot of other ways you could choose to split that data set. But in the paper, they tested doing this, and it worked quite well. They also tested to make sure that effectively doubling the size of the data set wasn't the reason why. So they kind of go into why the theory is that their algorithm works better, which we'll touch on in a minute. But essentially, it looks a lot like DPO. You start with your data set. It's just input data, in this case, of likes and dislikes. And then you have a starting model, which there's a little nuance here I'll explain in a bit. But you make a copy of that model. You have your policy model. And then you run KTO with your data set, and it makes the updates. It still has this constraint so that it doesn't diverge too far from your original model. It has a lot of advantages. So it matches or exceeds DPO performance. In the paper, they tested 1 billion to 30 billion parameter models. I'm sure there's a lot more work to be done here. Data is more available and easier to collect, right? Thumbs up, thumbs down, super easy. You don't have to overthink like, oh, do I like this one better than that one? You know, that's kind of a hard choice sometimes in some cases to make between two different outputs. And then it's resilient against inconsistencies within the data. It also has tunable hyperparameters for weight of what you like and what you don't like. And then this is what I was talking about with that starting model. KTO can work without supervised fine-tuning first. You do not have to start with a conversational model. In the paper, they were able to get really good results going straight from a pre-trained model using KTO and then turning it into an optimized conversational model, like all in one shot. And I think kind of like the robustness and the temperature sampling of DPO, I think that speaks to the quality of the algorithm, and it shows that they're really onto something here. Now, with those inconsistencies in the data that KTO is better at handling, we see in the paper here, KTO implicitly ignores noisy and intransitive data. And the theory behind this is that the math in KTO is going to tell the model essentially, hey, can't find anything really clear here to learn, like let's just move on. And so if you have those inconsistencies in the data, it's not going to have a negative effect on your final resulting model. So it helps the model learn what's important from the good, clear examples and kind of ignore the things that it can't seem to quite figure out. They do speculate in the paper that this may not be the ideal behavior for all training scenarios, but at least for what they tested on so far, it seems to perform even better than DPO. The hyperparameters include this beta, which controls risk aversion, two different lambdas. So there's a lambda D and a lambda U to control the weights on the desirable and undesirable examples. The paper recommends using these to compensate for imbalanced data sets, but you can choose any value. And I think it's cool that these allow you to tailor to your use case. So you can decide what's more important. Do I want my model to go and take chances, take risks because I need it to be creative, I need it to generate ideas? Or am I working on a use case where it's important for the model to be conservative, not to take risks? It's more important that it's never wrong than it comes up with some great answer every time. And there's going to be so many different models that we train that are used in the world. Conversational chat models, of course, but all kinds of different use cases as well, classifiers. And being able to control the model in this intuitive way for your use case, I think is a really nice benefit. I really like the way that KTO has been designed and implemented. So that about does it for today. I hope you learned something about these different optimization techniques. Maybe you have a better idea of how to apply one for your specific use case. If you like this video, please hit the like button or subscribe. I'm also interested in your human feedback, so leave a comment. Let me know if there's videos you'd like me to make on different topics in the future. I'm also building some cool stuff in AI myself. Check it out at entrypointai.com. Thanks so much.